Have you ever seen this comic? It shows up periodically on Reddit as one of those troll physics kind of things, but there's nothing fundamentally wrong with the concept. You just need a ball that's really dense and really elastic, and then you need a bear with ludicrously strong legs. I'm honestly disappointed that I haven't seen anybody build a robot that does this, bouncing a ball under itself to fly. If there's an object flying through the air and you step on it, you get bounced up, and the object gets bounced down with an equal exchange of momentum. When the object you just bounced off of eventually reaches the ground, it again exchanges momentum, but this time with the earth. In a way, the constant force that a person standing on the ground feels on their feet is just transmitted to the ground in discrete chunks through the bouncing object. As long as the average force remains the same, physics has no problem with this. However, because the ball, the bouncing object, also gains momentum at the top of its path when it bounces off your foot, it's not going to be following this nice parabolic trajectory of smooth arcs. If you wanted to do this for real, the ball would need to be moving so fast it would draw out basically a perfect straight zigzag line. Oh, kind of like that. But what if I told you this is pretty much how airplanes actually fly? This is a pretty typical spring scale. You might use it to weigh things in the kitchen. You can tell because it says kitchen scale right on the front. Now, if I put a 100-gram mass on our kitchen scale, we see that the meter ticks up a little bit. It's telling us how much this 100-gram mass weighs here on Earth's surface. Basically, it's telling us how much force the scale is pushing up on this mass with to stop the mass from accelerating downwards deeper into Earth's gravity well. What we just did, you might be able to consider a small-scale experiment. But I don't really want to do small-scale experiments. Today, I want to do a large-scale experiment. And for that, we're going to need a large scale. I thought it was funny. All joking aside, this is a very large scale. I'm going to talk more about how I built the thing in a little bit, but in a nutshell, it's a big foam core platform that is supported by 4 load cells at the corners that go back to an Arduino, that go back to that laptop that you're watching, with a live readout of what the scale is reading. If I take this 5-gram mass and I drop it in the middle of the scale, we can see that it wobbles around a little bit and then it settles to 5 grams. If I put it directly over one of the load cells, almost all of this additional mass is now being sensed by this load cell, but it still reads 5 grams. If I put it over here, all of the additional mass is basically split between these 2 load cells, but it still reads 5 grams. It doesn't matter where I put the weight. I'm basically averaging the force across the entire surface area of this platform. If I were to drive a vehicle over this scale, like this toy car, I could actually weigh the car while it was moving. The scale reads 0, then the car hops on the scale and we see the weight of the car, then the car hops off the scale. Big surprise, I know. Now, the freaky thing is that that also works with a paper airplane that's not touching the scale. As any object moves through the air, it has to push that air out of the way. And if that object is really strategically shaped, it can push most of this air downwards, which results in an equal and opposite reaction pushing up on the moving object, keeping it in the air. Typically, this process is referred to as flying. But that air that's been accelerated downwards below the wing, everybody always forgets about. Where does that air go? Well, it's moving downwards, it can't move down forever. Eventually, it hits the ground. And when that moving air reaches the ground, it can't go any farther. It stops. The air exerts a force on the ground, and the ground exerts a force on the air, decelerating the air. In this way, the total weight of any flying object is eventually transmitted to the ground. Like, by conservation of momentum, you cannot break that. The momentum's got to go somewhere. And this is true of anything that flies, from a paper airplane to a commercial airliner. It's just not obvious because those things are also normally moving laterally. Something that makes this clearer is like a helicopter, where there's obvious rotor wash and people walking around under a helicopter are experiencing wind. If I fly a quadcopter that weighs 250 grams over this scale, you can see that the scale reads 250 grams. And then I lower the quadcopter onto the scale, it sits down, and it still reads 250 grams. Like, it has to support its own weight. And the air coming down through the rotors of the quadcopter is transmitting the momentum that gravity would have given to the drone all the way to the ground so that the drone doesn't fall. Airplanes fly over our head every day, and we don't notice massive pressure changes when they go overhead. And that's because the affected air spreads out before it reaches the ground. We'll see in a minute that the weight of the plane is actually transmitted to the ground much faster than this smoke demo shows, but in general, after the plane passes through the smoke, you can see the smoke in the wake of the plane moving downwards towards the ground. But this signal widens out and spreads out very, very fast. In this case, we're spreading the weight of a piece of paper, about 5 grams, over an area that's actually much larger than this scale. Imagine that the weight of a real airplane in the sky at cruising altitude is probably spread out over many miles, meaning that the pressure change at ground level when an airplane flies over your head is minuscule. If someone threw this paper airplane at you and you ducked and it went over your head, technically there'd be some wind coming down towards your head from that paper airplane, but a human's never going to be able to feel that. This can. The first part of the scale that I worked on, because I knew it was going to end up giving me the most trouble, were actually these 4 load cells that hold the entire platform up. The load cell itself is actually just this bar. The rest of it is a 3D printed stand here just to give the scale some feet. Load cells are pretty cool. When you take a wire and you stretch it, that wire gets a tiny bit longer. And since longer wires are harder to cram electrons through than shorter wires, its electrical resistance actually goes up by a measurable amount. Likewise, when you push on the ends of a wire, it gets a tiny bit shorter and actually becomes a better conductor. Load cells work by exploiting this difference. When you push on this lever, the aluminum bar bends ever so slightly, stretching some of the tiny wires at the top and compressing some tiny wires at the bottom. And by the magic of ordering more than 4 of them, I've scraped all the silicone off of this one so that we can see all of those tiny, tiny wires that are actually getting stretched or compressed whenever the load cell bends. With the correct circuitry around it, that tiny change in resistance becomes an electronic signal that I can measure. So in this device, a force becomes a stretch, and then a stress becomes a change in resistance, and then a change in resistance becomes a number stored digitally on the microcontroller that's under there, and then I add up 4 of those numbers from each of these load cells that become the result shown on the laptop that is the one big scale measurement value. Of course, it's really unhappy now because it's like falling apart and I stole one of its feet. It's an extremely simple rig, but it still required an unfortunate number of wires to be soldered and code to be fiddled with. It's also important to mention, for the sake of the experiment, that there's a delay between the scale being loaded and the plot actually showing up on the computer. I'm recording weight data from the load cells at 80 Hertz, but the computer can only actually plot that at about 10 Hertz, and it's a variable update frequency. So in all of the clips where the synchronization matters, I've scooted the video of the laptop back in time by about 1/5 of a second so that everything lines up nicely. This platform is no slouch of a construction either. I started with a single layer sheet of foam core, but unfortunately, foam core isn't very stiff and the entire sheet could bounce, which really makes a mess of high-speed measurements. But it's not like I could make the platform out of something nice and stiff like metal or even wood, because it would weigh too much. The first issue here is one of precision. If the entire platform weighs 1 kilogram and I'm trying to detect changes that are on the order of fractions of a gram, then my measurement system needs to be better than 1 part in 1,000. If this thing was a lot stronger but it weighed 10 kilograms, then I would need to have a measurement system that was better than 1 part in 10,000. Honestly, despite the fact that this is a scale, I've never bothered to weigh the platform, so kitchen scale to the rescue. Whoa, oh, I'm hitting the ceiling. Okay, this weighs more than 1 kilogram, it zeroes out the scale. But then that puts the burden back on the load cells to make a precise enough measurement. The other issue is time delay. I'm not only working with very small forces, I'm trying to detect them fast. Imagine air hitting the top of this scale. If the whole scale flexes just a little bit to transmit that weight down to the load cell, that means that the tiny little force that I'm trying to measure has to be able to move or, slightly shift this entire platform that I now know masses more than a kilogram. Newton's second law doesn't lie, which means that if this whole platform needs to be accelerated by a very small force, but it needs to be accelerated very quickly, then its mass better be as small as I can get it. Now, if we want our platform to be extremely light and extremely stiff, it's best not to reinvent the wheel. What else needs to be extremely light and extremely stiff? That's right, rocket parts. This is going to be the most overkill segment of a video that I've ever done. Basically, if you have a flat sheet of material, like this piece of foam core, it's really easy to flex in the out of plane direction, because that's the thinnest direction. But if you tip it sideways and you try to bend this, you're definitely going to break it before you bend it. It's a much stiffer structure. But if you have a structure that you want to not flex in this direction, but also not flex in this direction, you can cheat. And make one of these. If you take your flat sheet of material that would otherwise be quite flexible in this direction, and you add a vane to it, this vertical strut that sticks up, now you've stiffened it in two different directions for a fraction of the mass of just making this a solid block of material with this square cross section. This is an actual part from an SLS tank, and you can see that in the real world, in the aerospace world, they mill these vanes directly into pieces of aluminum. So it's all one contiguous block where you've got this flat sheet, but that flat sheet needs to be strong, so they add all of these struts. I use hot glue, and after filming this segment, it seems rather silly to compare foam core hot glue to an actual piece of a rocket, but that is where I got the idea. So if I show you the underside of the platform, you can see that I basically just tried to orthogrid the whole middle and ended up adding some diagonal braces at the top to give more strength. I actually originally was going to put the load cells up here, and then I ended up putting them sort of in the middle. But yeah, these are all just 4-inch thick swaths of foam core that are serving to stiffen the entire back structure. It looks overcomplicated, and it probably is overcomplicated because I don't know exactly where I should put all the struts. But I kept having to add more struts because I wanted the structure to be stronger. Many sticks of hot glue gave their lives so that we could measure an airplane's weight while it was flying. Now that we have a very large and very sensitive scale that works, what we need is a paper airplane. What? Wait a minute, that's not the weight of the plane. What gives? Turns out that when I said when the air spreads out, I meant the air really spreads out, like a lot. So, despite being very large, the scale platform wasn't capturing the full weight of the plane. This scale is sensitive enough that you can blow on it from like across the room and get a noticeable signal. It will detect any air that is moving in the vicinity. Now, the really frustrating part is that if you have air that's moving next to the scale, it'll actually create a negative signal because that air goes down, spreads out under the scale, and ends up pushing up from underneath the platform. Needless to say, this was really frustrating when I figured it out. To fix this, I added paper on and off ramps to prevent air from going under the scale, and I added walls to sort of catch all the air affected by the plane and make sure that that air was actually getting measured by the scale. After a number of bad throws with poorly folded airplanes, why do they keep flipping over? I finally glided one down the middle. And we can see the scale reads a nice steady value. And if I just set the plane on the scale to find out how much it actually weighs at rest, it reads the same thing. It works. Now that the system works, let's do some analysis. My original script here was actually totally wrong. After my video about flying playing cards, I was used to looking at the downwash from a flying object coupled to these wingtip vortices. Long after the card has passed by, the air column it affected is still dropping down. These wingtip vortices do totally show up with paper airplanes, and they still look really cool, but they don't do what I expected. I thought that the spiraling downwash would carry most of the momentum the plane wanted to send to the ground. If that were true, the plane would fly over the scale, this sort of spiral structure would form, that spiral structure would slowly travel down to the scale, and then only once that spiral hit the scale would we actually see a reading. But the slow-mo says that's not the way it works. Here are clips from the side and the back at once. There are two different throws here, so the timing isn't perfect, but the disparity I want to point out is so large that that doesn't even matter. In the down the trench view, we see the plane flies through, hits the fog, and makes a spiral. Now, well after the plane hits the end of the garage, that spiral is just barely beginning to make its way down to the ground. Likewise, from the side, we hardly see any downwards motion of the air at all, but the scale is already reading something. Even if I don't do the time shift on the video from the laptop, making it like dramatically delayed, the laptop is reading something seconds prior to that swirly vortex hitting the ground. So if that swirl isn't what transmits the airplane's weight to the ground, what does? I think it's actually a very wide, very small magnitude motion of the air. If you take a big flat object and you push on the air that has fog suspended in it, it makes this really cool scrunching effect. This is actually happening every time that any object moves through the air, you just normally can't see it. Most interestingly to me, it makes this scrunching effect almost instantly. At the absolute fastest, you can send a pressure wave through the air at the speed of sound. I mean, that's kind of what sound is. It's a pressure wave moving through the air. And I think that an extremely low frequency push like this probably is moving at the speed of sound. I did a little bit of research trying to dig up whether the speed of sound in air changes noticeably when you get to infrasonics, like sub 20 hertz, really low frequency sounds. And it looks like there might be tweaks, but they're all second order effects. The speed of sound is pretty much just the speed of sound. It's not like it's gonna change by a factor of 2. After I'd started editing this video, I was really not happy with the lack of result here, and I went back to the garage to try to film something like this effect in high speed. You can totally see the air scrunch up when I hit this board with the hammer. I'm trying to create a very high frequency push so that it's something the camera can observe. At this frame rate, it should take sound, the fastest possible pressure wave that I can send through air, with this air pushing on this air, pushing on this air, pushing on this air, and so on. About 15 frames of video, or half a second at this playback speed, to travel 1 meter. Do you see the wave? Because I can't. I spent an evening trying to do some motion enhancement on these clips, and I just couldn't get there. After running this experiment, and after spending a bunch of time trying to do the motion enhancement, I actually did the math. And if I'm working these numbers correctly, in order to get a detectable 0.5 millimeter displacement of the fog with a 5 kilohertz signal, the sound pressure level necessary far exceeds this graph on Engineering Toolbox, surpassing the ow my ears hurt level and reaching the ow my lungs hurt level with almost 200 decibels of sound. Probably more than I can provide with a hammer and a piece of plywood. Qualitatively, I like to imagine a shadow of sorts, like a high pressure region on the ground below the plane where that plane's weight is being felt by the ground. If this signal travels down away from the plane very slowly, the shadow could be far behind the plane. But I think more likely, the pressure wave travels very fast, certainly faster than this paper airplane flying, and actually pushes on the ground pretty much directly below the plane. Without real hard evidence from the high-speed camera, and with a scale that only measures at 80 hertz, or every time the sound has already had the chance to move over 4 meters, I'm not going to provide a great quantitative answer for you here about where this shadow lives. But qualitatively, I hope it's a good mental model for understanding this problem. Frankly, because these signals seem to travel so fast, I'm surprised that the paper ramps to mitigate underflow do anything at all. It feels like the pressure wave would just push on the paper, and then the paper would push on the next bit of air. After all, you can actually hear sound through a piece of paper. But for some reason, this does work. One possibility is that the paper operates like a low-pass filter for sound waves, and the scale needs continuous air blowing past it to maintain a reading, because otherwise the pressure dissipates. I also ran some experiments with dropping paper, parachute style, towards the scale, and the entire weight of the paper didn't show up right away, and sometimes the measured weight was actually too large immediately before impact, in a way that would agree very nicely with a slow-moving signal piling up under the paper parachute like a really slow version of a sonic boom. With these weird results, I'd want to do a lot more experiments before saying definitively how fast the useful part of this pressure wave travels. If anybody out there wants to create like a grid of really sensitive pressure transducers that are multiplexed into an oscilloscope, recording at an effective like 100 kilohertz and then throw a paper airplane over that, I would be all about it. But even without super accurate phase data on these signals, we can learn a lot from looking at these graph traces. These measurements tell us something. I can hear some of you yelling at your screen right now. The plane is falling down through the air. It's not, generating lift. How are we getting the full weight of the plane on the scale? Well, even if it's flying downwards, even if it's flying at a descending angle, it's not accelerating downwards. If it were falling, it would be following a parabolic trajectory towards the ground, and the reading on the scale would be less, or even zero, if it was generating no lift, like this ball of paper without wings. Actually, that tiny blip at the beginning was caused by me moving my hand to throw it, and I could recreate that blip without throwing the ball. So the ball generated no lift and made no force on the scale. But here, the plane is flying in almost a dead straight line, which means it's supporting its own weight by pushing down on the air. If I fold the wings here to make the paper airplane pitch up, we can actually make the plane accelerate upwards against the force of gravity. And for that brief moment, the scale records a much higher weight for the airplane. And then the airplane stalls out, falls to the scale, and creates a really big spike upon impact. Since I actually overshot the y-axis on this test, I did it again with the scale zoomed out. During this peak acceleration, the scale reads about 15 grams. That's 3 times the weight of the plane. Then the plane begins to free fall, generating no lift. Then it impacts the scale, making quite a ruckus, but eventually the scale settles and we just see the actual weight of the plane at rest. Since this peak is 3 times the actual weight of the plane, if there were an ant that was a passenger riding this paper airplane during such a ridiculous maneuver, that ant would have pulled 3 Gs. This is the paper airplane equivalent of a fighter jet. Even in powered flight, if we were to attach engines to this paper airplane, unless the plane is accelerating up or down, unless the vertical component of its velocity is changing, then its entire weight is being transmitted to the air, and then the air transmits that entire weight to the ground down below. The only time this is not the case is when the plane and the Earth are accelerating apart or accelerating together. You can feel this on a plane. You sort of get pressed into the bottom of your seat during takeoff when the plane accelerates upwards, but then you feel totally normal despite the fact that the plane is moving up very quickly. And then at the end of the ascent, you can sort of feel a lightness as the plane levels off. But then again, once it's not changing its vertical velocity, it feels totally normal. In my last video, I was looking at the aerodynamics of playing cards, and I had a bit of an aside where I got really excited about how you could see the card push the air around it down, providing the equal and opposite reaction necessary to keep the card in the air. Now I think that this may not have been the correct air to look at. Although it does contain some of the card's transmitted momentum, it's probably a small fraction thereof, and I probably significantly overestimated the volume of the air moving at this average speed, and didn't subtract out the air that was moving up as a part of those wingtip vortices. Many comments also pointed out that I probably heavily overestimated the mass of the playing card in that example, so today we're going to fix that by weighing a playing card. No, sorry, not like that. We're going to throw a playing card over the scale. Now, the cards are even lighter than the planes, which were already difficult to see properly on the scale, so throwing cards over this scale is getting into the realm of some seriously gnarly signal-to-noise ratios. That means, among other things, I need the air in the room to be extremely still, and there can't be any cars driving by outside. This scale actually doubles as a seismometer, and a car on the road can generate noise that's larger than the weight of a playing card. I've stretched the y-axis so we can see the signals, but you can see that the signals we're getting are weird. If only I could throw one level and without hitting the scale. It's rattling the garage door. Yeah. This thing is too sensitive. I built a seismometer. I was able to get a couple throws that produced nearly square wave traces on the scale, but in general, many of them start with this big initial spike and then a signal that doesn't last very long, and I think I know why. If we actually look at the flight of the card, when it leaves my hand, my throw isn't very efficient, so the card has to redirect itself in the air. This acceleration requires a lot of lift, requires a lot of air motion, and makes a bigger impact on the scale, just for a moment. After this, the card begins to twist. If this card were face down, generating lift like it should, we wouldn't be able to see the face of the card in this clip. Once the card flips sideways, it's effectively in free fall from the scale's perspective, so the scale stops reading before the card is actually totally gone. These factors, together with the fact that I think I throw cards faster than planes, makes the cards really difficult to measure. So I did end up cheating and just setting one on the scale. And if you look really closely, the stable card throw weight and the card at rest weight are the same, and they aren't 5 grams. I'd rather be right about the intuition and wrong about the numbers any day of the week. At this point, I hope you've gained more of an appreciation for the conservation of momentum. Okay, so I couldn't leave it at large scale. The video's basically done. I could be at home clicking publish right now, but instead, I'm driving to the airport to do the experiment at full scale. The math says that it should actually be pretty easy, but I need to know if this can work, so here we are. So today I'm under the takeoff path for Raleigh-Durham International, and I brought a modified version of my large-scale experiment. And I'm gonna try to weigh a plane. Of course, because I can't capture all of the air pressure coming down off the plane, and I haven't built walls around the runway that are like a half a mile tall, I've needed to make some changes. Notably, the pressure getting under the scale and pushing up on it from underneath problem, I've solved by basically encapsulating the scale in this wooden box, which is nominally airtight. The top panel of this box and the bottom panel of this box are connected to each other by a load cell that can tell how much those panels are being squished together. So basically, I've made the scale into what it always wanted to be, a pressure sensor. In this case, I'm trapping a volume of air inside this box at a fixed pressure, and I'm using the force on this plate to compare the pressure I've trapped in this box to the pressure outside the box in the ambient air. The cool thing is that means it doesn't care if the box is right side up or upside down or sideways. You can think of this as an extra fancy barometer with a really large area to average over. Now we just have to wait for a plane. That one. Sound is here. It's probably a 45-degree angle. It's going straight overhead. It's a Delta. Straight overhead. See, that looks like a giant bump, but like, do I trust that it's the plane? I don't think I can trust that that's the plane. This, unfortunately, was pretty much the pattern for the rest of the day. All I walked away with was 100 gigabytes of myself looking bored and a great deal of uncertainty about what I just measured. There was a storm coming in later, and the buffeting wind and the continuously dropping atmospheric pressure were just too much for this little wooden box to handle. Another 20 minutes of this and I'm gonna get pretty bored.
3 days later.
So I went back to the vacant dragonfly-filled field to the south of the airport, except this time there was no impending storm, no wind to speak of. I was watching the planes approach live, and this time the planes were approaching from the south, so they'd be at a much lower altitude, giving me a larger and sharper signal to try to detect. But, unfortunately, the daytime dragonflies were replaced with evening mosquitoes. You can't see them in most of the clips unless I do the motion enhancement thing, but rest assured, they're there. Oh my God, I'm getting eaten by mosquitoes though. Did that do it? Oh, that totally made a spike. Oh, that's so cool. And this time, it worked. That little blip is 100% attributable to an airplane flying over the scale. And I know this because I measured similar blips a whole bunch of times. Here's a sampling of them. The weirdest thing to me is that negative signal that shows up in most of my detections. Oh yeah, that actually made an up and then a down. There's all sorts of stuff. I mean, if I had a scale that was miles across, I would expect to measure 100% of the plane's weight. I would expect to measure the entire force that the plane was exerting on the ground through the air. But I didn't have a scale that was miles across. I only had a scale that was about a square foot across. And that didn't stop me from trying to calculate the entire mass of the plane, using some extremely bad assumptions. So as the first of many grains of salt with which you should take this calculation, I arbitrarily chose a trace with a minimal weird negative signal. Then I needed to know what plane I was looking at and how far away it was. With a great thing called the internet, I determined this was an Airbus A320neo, which is about 38 meters long. Since it takes the plane 19 frames of video at 30 FPS to pass this tree branch, I know the plane was traveling at about 130 miles an hour, which sounds pretty reasonable. With this speed, a distance per second, and my data that was collected every 80th of a second, I can smear that data out as if it were projected on the ground below the plane over a few hundred meters. I could also just draw a line on the map to know that I was about 50 meters away from the runway line. So we have this one line of real data about what the pressure looked like under the plane, and all of this area to fill up with guesses about what the pressure would be if I had scales everywhere. Personally, I'm a big fan of Gaussians, so I fit this curve to an asymmetric Gaussian. Then I assumed that the sideways Gaussian had the same width. I don't know if that's a good assumption, but I said that there were many sketchy assumptions in this calculation. If you look at the combination of these two curves, that gives us a pressure shadow on the ground that looks kind of like this. Pretty cool what you can do to make a limited amount of data look just like what you expected if you basically just tell the data to look like what you want it to look like. Unfortunately, the fun ends there, because if you actually add up all this force applied to the ground, we get about 2 tons. Unfortunately, an Airbus A320 weighs a lot more than that, so my measurement wasn't very good. Also, if you, like me, saw all these plots together and thought, wow, they all sort of have a bump right here. What if this isn't the plane, but this is the plane? So I did some analysis, and that hypothetical flying object for this trace would weigh almost 900 tons. So no, considering my scale is more likely to underestimate, I think this tiny blip is probably the plane. There were some other sources of variability here, but I think the most important reason is that the tape could move. As the air pressure increases, it pushes on all sides of this box. It presses on this plate, presses on the sides, and it presses on the tape that goes around the edges of the box. This tape, which is intended to seal the plate against the external atmosphere, flexes in slightly, which actually compresses the air in the box. I'm trying to measure pressure changes that are on the order of like a part per million, which means that the entire measurement that I'm trying to make can be canceled out if the internal volume of this box changes by like a few cubic millimeters. And I'm pretty sure that a slight compression of this gasket tape around the rim is more than sufficient to do that. In what has to be one of the greatest anomalies in this channel's history, blue tape was not in fact the correct tool for the job. If I wanted to do this properly, I would need less flexible materials than even wood, probably. I would need to give a very, very, very slight clearance between the pressure plate and the rest of the box, and the gasket material would need to not be very flexible and minimize the amount of gasket material by getting the tolerances and everything else really, really close. And then, of course, I would want a lot of them spread out across the flight path so that we could map the pressure shadow of the plane with many, many traces instead of trying to extrapolate the whole thing from one. Anyway, I was super excited to have detected any signal with this scale, and I can say that, you know, although I probably had some systematic error in my measurement that I haven't yet accounted for, I was able to measure the weight of an airplane while that airplane was in the air. I think that's pretty cool. Now back to your regularly scheduled outro. At this point, I hope you've gained more of an appreciation for the conservation of momentum. Whenever an object is in the air, it's exposed to gravity, and if there's not something preventing it from falling, it will accelerate towards the ground. But if that object isn't falling, if it's just hanging there in the air, it has to shed this momentum that it would have otherwise gained into some mass that can be accelerated. And that mass is the air around the object being pushed down towards the ground instead of the object. Individual molecules of air bouncing in pressure waves between a plane's wings and the ground connect these two solid objects, pushing them apart, just like the ball from the meme in the intro. Thanks for watching, and I'll see you next time.